Okay, so here are the notes for section 2.1. So we're going to learn how to find the slope of what's called a tangent line. A tangent line is just a line that just grazes a graph, but only touches it at one point. And how can we find the slope of that line? So let's just look at this example right here, created by my colleague, Karen Cleff, who's the chair of the department. So let's say the function is f of x equals x squared. So we know at x equal to 1, y is equal to 1. Okay, so let's say what's the slope of the line that touches f of x equals x squared, one of the straight line that intersects with f of x equals x squared only at the point 1 comma 1. Okay, so let's say x is 2. So what we're gonna do is we're gonna find the slopes of tangent lines where the x gets closer and closer to 1. So let's say x is 2. So let's say the x interval is from 1 to 2. So we know that f of 2 is 4. Remember, it's rise over run. So we're looking at this table right here. Okay, so we see that table where it says x interval 1 comma 2, 1 comma 1.5. Okay, so let's say, so what's the slope of the line connecting when x is 1 and when x is 2? So it's rise over run, so f of 2 is 4. F of 1 is always 1. So in the first case, it's 4 over 1 divided by 2 minus 1, and we get the slope is 3. Now when x is 1.5, when we connect 1 comma 1 and 2.25 comma 1 comma 5, I'm sorry, the other way around, 1 comma 5, 2.2 comma 5. So remember it's rise over run, so the change in the y's, so f of 1.5 is at 1.5 squared. Yeah, so it's 2.25 minus 1 over 1, and the difference between 1 and 1.5 is 0.5. So then, now the slope is 2.5. Okay, so now let x equal, let's connect so let's say x is 1.2. So we're gonna find the slope between 1 comma 1 and if x is 1.2 and the y would be f of 1.2, which would be 1.44. In that case, the slope is 2.2. Now let x equal what? Draw, when x is 1.1 and you draw a secant line from 1 comma 1 and 1 comma 1, in the second coordinate would be 1 comma 1 comma f of 1 comma 1 or 1.1 squared. You get the slope is 2.1. And as you get closer and closer to 1, you see that the secant line gets closer and closer to 2. So we'll just say, that the slope, and it turns out that's actually the correct slope. We'll see, we can actually prove that later in the course. But if we just kind of look at the limits, it looks like it's approaching 2. So that's kind of a good guess. So that red line there in the document, the slope, that's the tangent line, and it has slope equal to 2. And we got that just by looking at the slopes of these tangent lines where the x coordinate gets closer and closer to 1. And okay, so the instantaneous velocity is actually the slope of the tangent line, and the average velocities are the slopes of the secant lines. Okay, so here's just now we're going to look at average velocity. Okay, so maybe if you've taken a physics class, you have learned that velocity is distance over time, but of course, if you have acceleration, the velocity is actually changing, right? So if you're going at a constant rate, the velocity is always the same. So let's say you have this distance function right there. If you can see an example 2. And we see that the distance function is given by minus 6t is time. And we see that the distance function is given by minus 16t squared plus 120t. And if you graph that, you get an upside down parabola. Okay, so let's see if we can actually find the average velocity at, the instantaneous, we're going to find the average velocity, because the average velocity is the difference in, basically you find the slope of the line connecting the two ordered pairs. So in this case, like what's when t is 1 and t is 2, or when t is 3, what's the slope of the secant line? So let's just start finding the slope of the line, the average velocity from t equal 1 to t equal to 3. Okay, so you plug in 3, you get 216, you plug in 1, and you'll get 104. And now just find the slope just find the slope of that line. And it turns out it's 216 minus, different, the rise over run, 216 minus 104 divided by 3 minus 1. So the average velocity, we go from t equal 1 to t equal to 3 is about 56 feet per second. Okay, so that's the average. But again, the velocity is actually changing because the distance function changes with time. It's not okay. It's not constant with time. Okay, so so now what is the average velocity when we go from t equal 1 to t equal to 2? Once again, it's rise over run. We take the difference in the distance traveled, s of 2 minus s of 1 over 2 minus 1. Well, s of 2 turns out to be 176 feet. S of 1 is 104 feet. So like in 2 seconds, you've traveled 176 feet. And 1 second, you've traveled 104 feet. Take their difference, and the difference in the t's is 1. So the average velocity when you go from time equal 1 to time equal 2 seconds is 72 feet per second. Now let's just say, instead of giving some number here, let's say the initial time is t equal to 1, and we want to, let's say we go some 8 seconds, additional seconds. So we saw this before in the last problem set. I know it was 1.2, or I think it was 1.1. And so let's say we start at 1 and we go some undetermined number, maybe h is actually typically small. So what's the average velocity when we go an additional 8 seconds? So we've gone 1 second, and then we've gone an additional 8 seconds. So there I'm at the top of this page here. So the average velocity is the distance function s of 1 plus h minus s of 1 over 1 plus h minus 1, right? Rise over run. Okay, so you just have to expand the formula. Remember, the formula for s was minus 16t squared plus 120t. And and s of 1 turns out to be 104. Okay, so you just look at that difference quotient and you simplify it. And I think you can see the algebra there. And it turns out to be minus 16h plus 88. Okay, and that's actually for at t equal to 1. Okay, so the slope of this, or the average velocity, if you from 1 to 1 plus h, where h is some positive number, the average velocity is given by minus 16h plus 88. Okay, and so yeah, that would just be the slope of the tangent line. Okay, and so now the instantaneous velocity is at some point c. This case, once again, s is, and you see it's there in the middle of the page. Okay, so again, it's just the rise over the run. So s is your distance function. So it's s of c plus h minus s of c divided by h. So again, that's just the slope of the line. And what happens if h gets really very small? Okay, so what would the slope, so what is that limit? Okay, so when h, what would the value be when h gets really very, very close to 0? Okay, so once again, let's just look at this rocket. Let's just look at the average velocity and then take the limit as x goes to h for, again, so let's say what's the instantaneous velocity at time t equal to 1? So before we found the average velocities near time t equal to 1. So remember, we found the velocity, the average velocity when we go from time equal 1 to time equal 3 seconds. And also the average velocity went from time equal to 1 to time equal 2 seconds. So what would that average velocity, what is the limit? If we get closer to 1, what would that average velocity be? And when the time is really small, that's what we call the instantaneous velocity. As we get closer and closer to 1. So, okay, so basically we evaluate the limit. Okay, so and that's actually the velocity. So the instantaneous velocity is the same as the velocity. So if we could just freeze time at t equal to 1, how fast? Let's say we were driving in a car and it was and the distance function was given by this formula. Okay, so what would your velocity be at time t equal to 1? Again, so you look at all the velocities, really, the average velocity is really close to 1. And as you get closer and closer to 1, what would that velocity be? So you take the limit as h goes to 0 of s of 1 plus h minus s of 1 over h. Or another way you can look at it, let x just be a number very close to 1. Like let just x be 1 plus h. Okay, so let's look at that average velocity, s of x minus s of 1 over x minus 1. And what is the limit as x gets really close to 1? And so just from looking at it numerically, just getting values closer and closer to 1. So we saw the average velocity from 1 to 2 was 72 feet per second. The average velocity going from 1 to 1.5 is about 80 feet per second. Let's say if we just go from 1, let's go another 0.1 seconds. Well, it turns out the average velocity is 86.4 feet per second. Now let's just go an extra, we go from 1 and then travel another 0.01 seconds. Well, the average velocity is about 87.89 feet per second. And I think, you can maybe just give a good guess and go, so the velocity at time t equal 1. So if you could just freeze time, okay, so time equal to 1, again, if the distance is given by that formula, minus 16t squared plus 120t, at time t equal to 1, your vehicle or whatever that you're traveling in, we were going at 88 feet per second. And of course, if you go a little bit more, the velocity is going to change because the distance function is not t times a constant. It's given in terms of t squared. Okay, so here's just a definition here. So the instantaneous velocity at a point A. So let's say you have some function given in terms of t. What is the velocity at time t equal to a? And this is actually turns out it's going to be the definition of a derivative, which we're going to talk pretty soon in the course. So derivative this is exactly what a derivative is. Okay, so how fast is this object traveling at time t equal to a? So if we could just stop at time t equal to a, how fast would we be going? And it's just the limit of the secant function when h is really very small. So it's s of a plus h, it's rise over run. Okay, s of a plus h minus s of a divided by h. Or another way of looking at it, what is the limit? Instead of h going to 0, just let t, time equal a plus h. So you've got 8 seconds plus a little bit extra. So let's say time is a plus h. So what is the instantaneous velocity is the difference of s of a plus h minus s of a over h, or it's also the limit of s of t minus s of a over t minus a as t goes to a, which of course, if you plug in t equal to a, the denominator is 0. So, but but the functions, for most of the functions we look at, that limit is going to be defined. Okay, so the average velocity is the slope of the secant line of a point near t equal to 1. And if we look at times time very close to t equal to a, we'll get the slope of what's called the tangent line. And remember, the tangent line is just the line that grazes the graph at a given time, like t equal to 1 at exactly 1 point.